Hello, everyone. Austin Lyons here from Creative Strategies and ChipStrat. So today we're going to talk about DeepSeek's Mixture-of-Experts paper and their V2 paper. Previously, we talked about DeepSeek's R1 paper, their reasoning model. And I started there because I thought, this looks like it could upend OpenAI's business. At the time, OpenAI was the only person with a reasoning model. And of course, it was proprietary. And so by having DeepSeek come out and essentially open weights, so share, not open source because they're not sharing the source code, but they released the weights, they wrote a paper, and they said, hey, everyone, we did reasoning too. Here's how you can do it. And so I thought, okay, that's pretty crazy. That's going to upend things, and that's playing out. This was a tweet from yesterday or so. Maybe it was a few days ago. I guess it was a few days ago, February 17th. So earlier this week, where Sam Altman said, hey, should we open source something? Should we open source O3 Mini, our reasoning model? Now, of course, that's pretty crazy because even though their name is OpenAI, they are closed proprietary AI models. And now, because of DeepSeek, Sam Altman's coming out and saying, hey, I guess we don't need a proprietary reasoning model because DeepSeek can already do it and they're already giving it to the world. So let's give ours out as well. And hence this, O3 Mini model, which of course, then using DeepSeek's paper, people could take this O3 Mini reasoning model and distill it down to phone-sized variants. Now, although the reasoning model was crazy interesting, if you recall, investors, everyone kind of freaked out. Nvidia's stock, their market cap dropped by like $10 billion or something. And that was like a month ago or so. And a lot of that freak out was actually due to DeepSeek's V3 paper, not their reasoning model, but their sort of like thinking fast model. And specifically in there, they said, hey, we trained this using only $5.5 million US. Well, anyway, I wanted to unpack the V3 paper and really think through from first principles, what did they do? What did they show? And does this actually mean we should expect, less compute demand? So Microsoft backing off spending $80 billion a year in CapEx. Now, as I started reading the V3 paper, it referred to all these other papers. So you kind of needed all this other context. So instead of studying the V3 paper, I thought I would take us through V2 and the papers that led to V2. And note that these papers are all from 2024. So V2 was in June 2024, I believe. And a lot of the papers that it builds upon were actually released back in January of 2024. So just over a year ago. All right, so this is some quick context for anyone who's new. If you kind of know a lot of the basics already, you can fast forward through some of this. But in DeepSeek's paper, in the first paragraph, in the V2 paper, they really emphasize that, hey, we've noticed something. As models we learned from the pre-training scaling laws that if we have bigger models with more training data and more compute, we can get more intelligence. Of course, the problem is to get that more intelligent, you have to have a bigger model, and a bigger model means worse inference throughput and potentially latency. So worse inference speed. And what does that mean? That just means it's a worse user experience. So when you ask ChatGPT to help you, the smarter it is, the bigger the model it is, the longer it's going to take to respond. That's basically what they're saying. So they said, and by the way, it comes, of course, as more demand, like compute needed during training. And of course, this is a problem for DeepSeek because they're in China and we have export controls. So the United States is trying to prevent China from getting compute to do this exactly type of AI training. So I wanted to quickly unpack. It's like a key important thing to understand that as the model size increases, the inference speed decreases, and you might wonder why. So really quick, if you recall, and if you don't know anything about neural networks, that's fine. I got this. I always use the wrong hand. I got this screenshot from videos on YouTube. There's this guy, three blue, one brown. He makes all these amazing videos to explain lots of cool math stuff. And so he walks through neural networks. And I just took a screenshot of this to show you that at the root of it, neural networks are all represented by matrices. And it's just matrix math and matrix multiplication and addition. And specifically, you can see here that this neural network is represented by a weights matrix that represents like the strength of the connection between all these different neurons. Those circles are neurons, and sort of the column of neurons, each refer to like a layer of the neural net. So you've got this weights matrix, And I just wanted to give you a visual illustration here that if we increase the size of the model, what that means is increasing that neural network there on the left. So for example, having more neurons in a particular layer, which if we add more neurons to layer, that would increase the size of this weights matrix, because there would be increased connections because there's more circles. So you'd have to represent all those essentially more of those lines. Those lines sort of represents the weights, how strong should this connection be? So if we were to increase the number of layers, it would increase the weights matrix. If we increase the number of neurons in a layer, it would increase the weights matrix. And then, of course, also increasing the number of neurons in a layer would increase these are called the activation vector and this bias vector. None of those details matter. All you have to take away is if we make that neural network bigger, these matrices get bigger. And why does that matter? Well, so matrix math, at the end of the day, it's just lots of multiplication and addition. And so if you have this 2x2 matrix, if you remember this from any of your math classes, you just kind of go through, and each of those entries, you have this matrix with 4 entries, and each entry is a dot product. So multiplication and addition. And if the matrix grows, there's just one more additional multiplication and addition you have to do to get that 58, 1 times 7 plus 2 times 9 plus 3 times 11. So the point is, these are all matrices. Matrix math is actually just a bunch of dot products, which is simply just multiplication and addition, things that computers can do really well. And if you increase the size of the neural net, that you'll increase these matrices, and that just means more multiplication and addition. And at the end of the day, these are just more operations that have to be done. It's just more math. So it could be floating point operations if it's in the cloud, and if it's at the edge, it's probably just integer operations. So more flops or tops are needed. And one cool thing is that with AI accelerators, GPUs, NPUs, XPUs, whatever, they can do this matrix math really fast for 2 reasons. One, of course, you notice that each of those dot products in the matrix can be done independently. So they can all be done in parallel. So these GPUs have thousands of multiply, accumulate units that do these dot products. And so all I have to do is a ton of these MAC units, little circuits, and you can suddenly do big matrix math in parallel. So you can do them very quickly. And so all you have to know is that when the matrix grows, if all those MACs aren't utilized, then you can just utilize more of them. But if you're already utilizing all of them on a particular clock cycle, it means you have to take another clock cycle to finish up doing all that extra multiplication and accumulate. And what that simply means, all of this is to illustrate that bigger neural net, bigger matrices, more multiplying and accumulation, which could mean more clock cycles or longer inference time, longer latency. And by the way, LLMs grows quadratic scaling. As you increase the dimensions, the amount of flops needed scales quadratically, both in the feed-forward network that happens, just that pass through the layers during inference, and then also in the self-attention mechanism, which is kind of where the LLM looks at like the whole sentence, for example, to get the context of what does this word mean. Again, layman's terms, if you increase the model size, it can drastically increase the amount of flops you need and drastically decrease the user experience. Okay, so mixture of experts. So there's the question then is that's highlighted in the V2 paper is, hey, can we get more intelligence without necessarily needing bigger models and therefore more flops or worse inference time? So DeepSeek V2 was a mixture of experts model. They had previously actually done a paper with just their first dense model, 67 billion parameter model that was performant on the order of what at the time was state-of-the-art open weights Llama 2 and also competitive with ChatGPT 3.5. So already a year ago in January of 2024, we should have all been saying like, holy cow, here's a Chinese lab, probably with less compute, is able to make and share for the world, competitive dense model, competitive with both Meta and OpenAI. Already there's a bunch of business model questions and just really interesting things that come to light there. But anyway, Now, DeepSeek improved on that original dense model with a DeepSeek Mixture-of-Experts model. They use that Mixture-of-Experts architecture in V2. I wanted to quick cover Mixture-of-Experts for those of you who don't know. Again, if you know that, you can fast forward. So this is a screenshot that I took from a 1991 paper, Adaptive Mixture of Local Experts, by a bunch of sort of the AI forefathers, if you will, including Geoffrey Hinton. And the key insight here is, instead of using the entire network every time, what if you could actually just have little networks that are experts in a certain thing, and then during runtime, you choose which expert to give the question to. And so, my mental model here for this was trivia night. If you have someone that's like the science expert and someone that's the sports expert, someone that's like the pop culture expert, instead of everyone having to train for trivia night on all the world's knowledge, you could just say, hey, just focus on sports trivia, sports guy. So that's my mental model for expert networks. Now, why this matters is, and as we'll see I'll just go to the next slide. So Mistral was the first to publish a Mixture-of-Experts paper. I think they announced it in December of 2023, but they shared their paper in January of 2024, so a year ago. And what Mistral showed with their Mixture-of-Experts was they had 8 experts, and what they would do is, for each token at each layer of the neural net, they would choose 2 experts at runtime. So they'd have this, they'd give the input, it'd go to this router. The router would kind of know which subset of the network, which expert to choose, and it would give that input to the 2 experts. Then it would combine their output, and that would be the output. What's cool about this is, even though I think they had a 47 billion parameter model, so they had to load all that into memory, but at each sort of activation step, the way I think of it is, they would light up 2 experts instead of all 8. So they would only use, I think it was something like 13 billion parameters out of 47 billion. So when they're doing this inference, when they're doing all of that multiplication and addition or accumulation, instead of needing to do that for 47 billion parameters every time, they only needed to do it for 13 billion parameters. So something like they only needed 25% of the floating point operations. So that's, and you remember the quadratic scaling, right? So that's like significantly higher throughput or a better inference experience for users. So that's Mixture-of-Experts. This was Mistral's architecture. Now, I think something like 3 days after Mistral published their Mixture-of-Experts paper, DeepSeek published their Mixture-of-Experts paper, and it was even more performant than Mistral's in that it used an even smaller subset of the total network for each expert. So instead of something like activating 25% of the network on each step, it was much smaller. I can't remember. It's like 13% or something. And how they did that is DeepSeek had the insight that, hey, in traditional Mixture-of-Experts, a lot of these experts or sort of subsets of the network have duplicated knowledge. It'd be like telling the sports and trivia people, like, hey, focus on sports trivia and science trivia people, like, you focus on sports and you focus on science, but they both also kind of know a little bit about each other's, and we're kind of studying each other's sort of areas of expertise. And DeepSeek said, no, that's inefficient. Like, I really want you to hyper focus. And so they came up with 2 innovations: fine-grained expert segmentation. That is what you'd think it would be. It'd just be like, how can we make these experts even finer grained, kind of even reduce their scope further? And then shared expert isolation. And I thought this one was pretty cool. They basically said, hey, it's almost like having another expert. They said, let's have a part of the network that's just covers all the general knowledge. So, hey, science person, like, don't worry about general knowledge, like, I don't know, information about the United States and days of the week and calendars and things like that. Just focus on science. And so they made this shared expert that would take all of the generic questions. And through this, DeepSeek was basically able to get rid of all this sort of redundancy across the network, which is how instead of having to have 25% of the network active at a time, they could whittle it way down. And so this illustrates it well. This is from the DeepSeek Mixture-of-Experts paper. You can see that they started with a smaller model. So there was a 16 billion parameter model, and they could get the performance of Llama 2 7B. So it took them more parameters to get the dense 7B performance, yet they only needed to activate, this was like 2.8 billion parameters. So that was what, like, I don't know, 10 less, I don't know, what math is hard for me right now, but something like 10% would be 1.6 billion. So, 18%, they needed to only activate like 18% of their network. And obviously that meant that it was going to be have a lot higher throughput and just have a lot better inference efficiency than Llama B. So again, this DeepSeek Mixture-of-Experts 16B, it was bigger, it had more weights that had to sit in memory, but it could run much, much faster. And I don't think I put a slide on it, but basically you can also train these in a much more efficient way because let me go back to this slide. All right, let's say when you're training, what you do is you do inference. So you light up these two, expert 2 and expert 7, and you get an output. And then you take a look at that output, if it's good or if it's not good. And if the output wasn't very good, you go back and you tweak the network and sort of say, this is what back propagation is. And you use gradient descent. And you basically say, hey, those weren't great answers. I'm going to tune all your knobs a little bit so that you would give a better answer, or not answer, but prediction next time. Well, if this was a dense model, you'd have to go to every neuron and tweak all of them. But with Mixture-of-Experts, in some sense, because you only sort of lit up expert 2 and expert 7, they were the only ones that responded. And so if the output's not correct during training, when you do back propagation, the gradients would only have to flow through expert 2 and expert 7. So you'd only have to tweak those and tell them like, hey, science guy and sports girl, you two were wrong by a little bit. Tweak your answers. Not only is inference more efficient, but actually training is more efficient too. Now, you do have to train the router, and so there's some overhead, but it's still much more efficient for training than having to train a fully dense model. DeepSeek V2. So we talked about Mixture-of-Experts, now DeepSeek V2, which was built using the Mixture-of-Experts architecture. So not only was it built on top of MoE, but it introduced several innovations that were all ultimately around having strong performance, but very economical and very efficient. I don't think I mentioned the V2 paper name yet. I don't remember if I did, but it's like in the title of the name. Let me look it up over here. V2, a strong, economical, and efficient Mixture-of-Experts language model. So they're, hitting home that they're trying to be very efficient here. And again, it's a little weird that in January of 2025, everyone freaked out about V3 being super economical and efficient. But this was literally in the title of the V2 paper, and that came out in June. So why was everyone freaking out then? Okay, so one of the big innovations was in the self-attention mechanism. They came up, the original self-attention used multi-head attention. And you don't need to know all these details, but basically people tried different ways of doing attention because you have to have this big KV cache, which stores up memory, HBM, or RAM if it's at the edge. And so the question was, can we do this group query attention or multi-query attention? Are there ways that we can try to reduce that KV cache size? And DeepSeek came up with an innovation, and they call it multi-head latent attention. I won't explain it, but basically it just compresses the KV cache. It results in a much, much smaller KV cache, which ultimately lets V2 have a much longer context window because the size of the KV cache scales, I think it's quadratically as well, with the length of the context window. So, and what is a context window? That's like sort of the working memory of the LLM. So you can think of it as the input length, but then also sort of the intermediate thinking that it's doing or reasoning. If you can have a much more efficient KV cache structure, you can support a lot longer context window because it doesn't blow up your memory as much. And that essentially gives the LLM more of a working memory. So instead of saying, hey, I can only read a 4-page PDF, now ChatGPT might be able to say, or DeepSeek in this case, would be able to say, like, I could read a 100-page PDF. Because of they call it MLA, multi-head latent attention. Because of MLA, they were able to have a more optimized KV cache size. And because of that, they were able to increase their context window from 4,000 tokens to 128,000 tokens. And I just like this screen shot that I put in here, where basically to test the efficacy of their context window through this needle in a haystack sort of game, if you will, where you pass in really long context and then you ask a very specific question. So you see if it can like find the needle. So 128,000 tokens is equivalent to like 100,000 words, which is roughly the length of a Harry Potter book. So it'd be like feeding an entire Harry Potter book and then going to page, 212 and looking and asking a very specific question. What color was Ron's shirt on Christmas? DeepSeek V2. So far we've covered that it's a mixture of experts. So you can unlock high intelligence, but only have to activate a subset of the network and therefore have higher throughput inference. Higher throughput means you can calculate many tokens at once, so you can support many concurrent users, for example, if you're serving inference at scale. So anyway, mixture of experts is efficient and performant inference and also efficient training. Basically, you use fewer GPU hours to get the same level of intelligence because you don't have to sit there and update a dense network. You have a sparse network to update. And then they also introduce the multi-head latent attention, MLA, which allowed them to have a very small cache size. With the performant cache, they could basically blow it back up for the trade-off of getting a really long context window, which is essentially giving it the long working memory and just making it more usable. So not only is it like smart and performant, but it's just like more usable because you can throw a bunch of documents at it, for example, when you're trying to do something interesting, ask some questions, do some analysis. And then on top of it, in V2, and actually they did some of this in the MoE paper as well, you can't forget the context around DeepSeek being a Chinese lab, not having access to the same compute that the labs in the United States have. And in this paper, they mentioned that they had H800s. But basically, DeepSeek had access to A100s, which was a previous gen Nvidia chip. And then our export controls came out, and what was that, like October of 2022, maybe? And the United States basically said, they kind of drew a line and they said, oh, people can't have chips, beyond this level of performance. And so Nvidia created a new SKU for Chinese companies, and they called it the H, so Hopper. So it's still Hopper family. So it was the next generation Hopper. A stood for Ampere. So Hopper 800, which was very similar to the Hopper 100. As far as we know, it's like all the same compute, the same number of multiplication and accumulation units in there and everything. It's just that the chip-to-chip bandwidth communication was cut in half. So instead of having a big pipe that lots of data could flow through, it had a much smaller pipe, so not as much data could flow through. And why that decreases performance is because then at the end of the day, all these little cores on your GPU, like you want them fully utilized. You want them to be doing math all the time. But if they're sitting around and waiting for inputs, then they're just idle. And so decreasing the bandwidth, making that pipe smaller and letting less data flow through just means they have to wait longer before they can do their math. So effectively, it's decreasing the performance. And that's like an easy way for NVIDIA to do it. Anyway, DeepSeek let us know that they have to use H800s. And therefore, as I mentioned here, sort of necessity is the mother of invention. They were forced to say, how can we overcome these constraints that were forced upon us? Because we still want to be able to train and inference. We want to be able to train, leading edge models, and we want to be able to inference them in a performant way. We want to overcome those constraints, essentially. And so I don't think I spell it out here. You can check in the paper. But they did lots of clever, DeepSeek came up with lots of clever load balancing algorithms. They call it device limited routing. So they did some routing and load balancing. So device limited is saying, like, can we be smart about not sending information to another GPU if we don't think we actually need to? They did a token dropping strategy, which is like, if this isn't that important to the overall prediction, like, let's just not compute it. And they also wrote that they did some computation performance improvements. So they mentioned making faster CUDA kernels with fused linear computations. And so we won't get into all that, but all you need to know is that even as far back as DeepSeek V2 and a little bit even in DeepSeek MoE, the DeepSeek team was already showing that they were willing to roll their sleeves up, get their hands dirty, and do some optimizations to try to overcome the constraints we put on them. Now, why this is super interesting is because American labs and Western labs didn't have to do any sort of optimization because they were just throwing GPUs at the problem, right? It's pre-training scaling. Get as many GPUs as you can, get more data, more compute, and go and try to race to the next model. And so no one is trying to optimize anything. Frankly, you're wasting your time, right? Because it's just like, buy more GPUs, don't optimize them. Now, DeepSeek didn't have that option. So they had to go and do the hard work of optimizing. And of course, it's a great thing for all of us because they're open weights and they're sharing that with the rest of the world. So basically, they're sharing those R&D innovations, that intellectual property, and saying, hey, OpenAI, hey, Meta, hey, Google, DeepMind, none of you guys are optimizing anything yet, but we figured it out, and here's what we did. Feel free to follow suit. So that's actually good for the rest of us because it means that all these other labs like OpenAI and whoever should be able to take these optimizations and optimize as well and try to get, for their fixed cluster size, eke out even more performance, even more utilization. So for their installed base, for that silicon that they already have, how can they get more out of it? Training efficiency. I covered this a little bit, but what the V2 paper said was that DeepSeek, for their dense 67B model, for each trillion tokens, it took 300,000 GPU hours. But for their Sparse Mixture-of-Experts V2 model, with all of their MLA and their all their other little innovations, routing and communication innovations and whatnot, they only needed 172,000 GPU hours. So basically, they needed 40% fewer GPU hours. What does that mean? That's awesome. It means faster iteration speeds. What it means is, for your compute cluster, instead of having to spend, in this case, for example, instead of having to spend 3 weeks to train something, what if you could train something in 1.7 weeks? It's faster iteration cycles. This is the kind of stuff that gets misinterpreted as, oh, people will use less compute. They're going to buy fewer GPUs. If they had 3 GPUs, now they only need 1.7. That's not the correct interpretation, because we're not at a place, again, and I covered this in my last video, like we're not at a place where everyone's happy with our intelligence ceiling. So they're saying, hey, how can we do this more efficiently? How can we have fewer GPUs? What we're saying is, like, we got all the GPUs we can afford right now. Can we get even more intelligence out of them? Can we run inference and serve even more customers? So this is on the training side of things. This is, hey, how can we run these iterations and these experiments even faster so we can learn even faster instead of, instead of taking 3 weeks, it took 1.7 weeks. There's so much in this V2 paper. It's crazy. That's why I want to unpack it. They also introduced other inference optimizations, so namely the FP8, and you can go look up quantization. Basically, instead of using a lot of extra precision with like FP16, which makes every multiply and addition take longer, without significant loss in intelligence performance, prediction performance, you can use FP8, so you can use like half the bits. And so your math is now faster. So they used FP8 precision. They did KV cache quantization, so similar tricks to the KV cache. It led to significantly improved throughput, 5.7 times the max generation throughput of the dense model. So at the end of the day, you can think of this, one way to think of this is they could serve 5 times as many customers with the same compute size, concurrent customers at a time. So in summary, what DeepSeek V2 showed, building on Mixture-of-Expert innovations, is with their V2, they had comparable performance to Llama 370B with much fewer activated parameters. So you see is like roughly 20 billion instead of 80 billion. And summarized on the right, that meant their training was 40% faster. Their KV cache size was way smaller. They could do way longer context windows, and their throughput was much, much higher. And this was all figured out by June of last year. So I wish I'd have been paying attention to all that interesting stuff then, but I am now. So if you go check this out at chipstrat.com, behind the paywall, I go into much more detail about what does this mean for training compute demand? What does this mean for inference compute demand? What does this mean for the Chinese AI lab business models, Alibaba and others? How did DeepSeek 2 impact them and their pricing? And what does this mean for American AI labs? Not only how does this impact OpenAI's business model and pricing, but what does it mean for their competitive advantages? Is compute a competitive access to hyperscaler compute through Microsoft and now I guess Stargate? Is that a competitive advantage or as much of a competitive advantage as it once was in light of DeepSeek? Also, is talent as much of a competitive advantage for OpenAI as it once was? And if it wasn't, then why did they have what seemed like a talent advantage? Were there just other first mover reasons why that was the case? And then, of course, also there's questions for open source competitors. Meta. Does this put pressure on Meta, and why? So if you like this, you want more of that, go to www.chipstrat.com and check it out. Thanks for following along. And of course, comments below, like a good YouTuber. But I do respond to them. Thanks.